speaker is Russell Hendel from Towson, who will speak on sums of squares, and we can all read. Yes. Russell, please.
Okay, so that's the title of my talk. There are two titles. I'm going to prove something about the sum of squares of the first n+1 k-nacci numbers. The results are known, and I'll show you in a second the outline for k equal 2, 3, 4, and 5. But then I'm going to use that as a piggy bank to discuss the way we deal with identities. I think we've spent too much time proving individual identities, and there have been several papers in recent years where we prove things for families of identities. And the reason this isn't commonly done is people don't have methods. So this paper is a very good example of how you can have these super duper methods that will prove things for individual cases, but not for general ones. And I've been working on some papers recently in which I've proven things for entire families, and the methods are very simple and elegant, and it suggests a different trend. So I will be mentioning that. So I just gave you the outline, but let me just say again, I'm going to tell you the problem. Sum of squares. So if you want, think of the sum of the squares of the first n Fibonacci numbers. This is a statement about the generalized Fibonacci numbers. So it's a statement for k equals 2, 3, 4, up to infinity. The examples will look at 2, 3, 4, and 5, which are known, and I'll throw in 6. Now, what you usually do with discrete with recursions is you look at them, you find a pattern, and prove it. Well, finding the pattern here is not obvious. And I had spent most of my time, several dozen hours of programming, saying, why can't I see a pattern? And there didn't have to be a pattern. Some of the methods use algebraic numbers and all types of things. There's no reason to expect there is a pattern. The patterns are surprisingly linear and as simple as you can get. Once you discover the patterns, you have to prove a main theorem. And proof methods used till now simply cannot give a uniform proof. I have something called the algebraic verification method. There's actually no work to be done. So it's a proof from the book. I mean, if you like, it's like creato ex nihilo. I'm creating a proof out of nothing, and I'll show you what that means, but it's very concrete. And then I'm going to talk about possible new directions for identities. So we'll begin. Everyone knows the recursions for the generalized Fibonacci numbers. Each member of the recursive sequence is the sum of the previous k members. K could be 2, 3, 4, 5, etc. What about initial conditions? Well, there are a variety of initial conditions. The first k minus 1 are 0, and the k minus first is 1. And I'll show you examples, and then I'll mention alternatives. My screen's jumping. For Fibonacci, you have 0, 1. For Fibonacci, you have 0, 0, 1. For Tetranacci, you have 0, 0, 0, 1. Here, the 2 is the sum of the 2 previous ones. Here, the 7 is the sum of 4, 2, and 1, previous 3. 15 is the sum of 8, 4, 2, and 1. And these are well known. These are the OAIS sequences. I'll just mention these are called generalized Fibonacci numbers. They're called k-Bonacci numbers. They're called k-nacci numbers. They have a variety of names. I found papers that give 5 or 10 names. There's no standard name. So I'm just going to call them the FK. Even for initial conditions, some papers begin with 2 1s. I've started at 0, but you could start at minus k minus 1. That's very common, so that f of 1, independent of k, is always 1. There are a lot of variations. The nice news is my theorems are independent of initial conditions, so I really don't care, and I'm just taking these. Okay, those are the k-nacci numbers. Here's my problem. Find the closed formula for the sum of the first n+1 squares. So with Fibonacci's, it would be 1 squared plus 1 squared plus 2 squared plus 3 squared up to fn squared. And I'm going to be using G when k is fixed, because I just don't like the FK upper I notation. So you can naturally ask what is known, and here's what's known. I hope you can read this. For k equals 2, the result is very well known. Lots of proofs. You can find any standard book on Fibonacci numbers. Cauchy comes to mind. Bauer comes to mind. It's probably in a lot of books on discrete math. Otsuka and Jacob Zik, I can't pronounce the names. Otsuka proposed a problem in 2012 in the Fibonacci Quarterly. Fibonacci Quarterly has a very nice problem section. What's nice about it is that the problems can turn into articles, and Jakubovic actually proved it, and that was in 2013. They proved it by algebraic methods. Schumacher in 2020 published a paper, and he proved this by generating functions. That actually motivated this presentation because he had 3 pages of algebraic manipulations, and I said, oh my goodness, there must be a simpler way. Then I posted this on archive, and some people pointed out other things. Before the case 3 was done, case 4 was done. That was Schumacher in 2019. And then there's a very nice paper by Prodinger and Selkirk. I complain a lot about how difficult generating functions are. They have a very nice paper showing if you have a good software package, you don't have to worry about them. Everything's straightforward. And they give the case 5. They did some manipulations, but it's probably equivalent. And I just threw in 6 to show I can do something. Now, I don't have room on this slide, but the obvious question is, okay, you have examples for K2, 3, 4, 5, and 6. What is the obvious pattern? So I stared at this, and I can throw in 7, 8, 9, 10. I think I went up to 14, and it's very perplexing. You can see some obvious things. The constant here is 1, here it's 0, here it's 2, here it's 3, here it's 4. Okay, I found one thing. The interesting thing here is these denominators, 4, 6, 8, 10, make sense, except everything is even here. So the denominators were actually 4, 3, 8, 5, etc. And I had to adjust them. But look at the coefficients here. Is there anything obvious about them? And the answer is no, and you just sit there and look at them. And so this took me a while. And when you deal with Fibonacci theorems, there are 2 parts. One is discovering it, one is proving it. Sometimes the proof is simple, sometimes the discovery is simple, sometimes they're both hard, as happened in this case. So, so this is the joke. You see the pattern. I mean, it's a rhetorical question, but here is the key. I'm sorry, my screen jumps around, but the denominator is going to be 2k minus 1, 2, 4, 6, 8, 10. I'm going to look at the diagonal elements. This is gn plus I, gn plus j, where j equals I separately. I'll make a little table and you'll see the pattern. Then I'll look at the remaining coefficients and you'll see the pattern also. So if you break this up into 2 parts, you can see the pattern. Now, let me show them to you. Let's just see here. This is the coefficients gm squared, gm plus 1 squared, gm plus 2 squared, etc. Now, if you look at these, well, this is 1, 2, 3, 4. I see, you can see that easily. These are negative, but look at this. 0, 4, 8, 12, 16 is linear. Slope is 3. Slope is 4, which is 1 more than 3. 1, 6, 11, 16 is linear. Slope is 5, which is 3 more than 2. 2, 8, 14 is linear. Slope is 6, 3 more than 3. 3, 10 is linear. 7, slope is 7, 1 more than 4. So this really has a very simple pattern, which you don't see it unless you know to look at it. Now, these are the tails of the coefficient for just the case k equals 6. And when I lay it out like this, you can see the pattern. You have 2, 4, 6, 8, 10 here. 5, of course, is 6 minus 1. And here you go backwards by 2. 2, 0 minus 2 minus 4 minus 6. Here you go backwards by 4. 4, 0 minus 4 minus 8. Here you go backwards by 6. Here you go backwards by 8. Here you go backwards by 10. So just to show that to you, the point here is there are patterns, but they're not obvious. So after you get rid of the square terms, you have minus 6, minus 4, minus 2, 0, 2. Then you have minus 4, 4, 0, 4. Then you have minus 6, 0, 6, 0, 8, and 0, 10. So those are the patterns. And now I can at least formulate a theorem. Let's just see here. We need coefficients for each product, gn plus I, gn plus j. And so this is what we're going to have. The denominators will be 2, 4, 6, 8, 10. It'll be 2 times k minus 1. The denominator for the special case, the numerator for the special case of 0 will be minus k minus 2. I wrote it for the square terms this way because I wanted to emphasize that slope of I plus 3. But an associate editor on OEIS suggested a much simpler form, which I'll share with you in a second. And this is that form where things go back. These are even numbers. 2, 4, 6, 8 multiples of 2. It just formulates what I did in the last slide. So if you look at the last slide, that's what it formulates. And so Peter Lushny, instead of using this, likes I plus 3 times k minus I minus 4. And this is nice for seeing patterns in there. There are certain axes of symmetry. But the important thing is it's quadratic. It's quadratic in I. I'll mention also that Howard Cooper in 2011, so a lot of people have studied these squares of Fibonacci numbers. He was interested in imitating the case 2 result, which is gn plus 1, but the point is, or gk plus 1, but he had this extra term there which he didn't simplify. So here's the theorem. For k equal 2, let gn equal fnk. It's a recursive sequence. Those are the generalized Fibonacci numbers. Each one is the sum of the previous k, and you start with any initial conditions. The sum of gi squared is a summation over all ij in the 0 to k minus 1 rectangle. Gn plus I, gn plus j has the coefficient nij over dij. Actually, this should just be dk, because dij is independent of I and j. This is not wrong. It's just can be made simpler. It's just dk, and it's 2k minus 1 plus c. And if you use the standard initial condition, c is minus nk minus 1 k minus 1. But the point is, this theorem is true no matter what initial conditions. I'm not doing any computation, so the initial conditions couldn't possibly matter. So let's just summarize. I've told you my problem. I've given you examples, discussed the literature. I haven't discussed proof methods so much because I'm going to discuss in the second part. I told you about my struggles finding the pattern. Here's the main theorem. Now, the proof is going to be very, very simple, and that's my contribution here. So given fixed k greater than or equal to 2 and n greater than or equal to 0, we must show the following equality. Well, as you all know, if anyone's ever taught discrete math, if you want to prove something for all n for a sum, you take the above equation with n replaced by n minus 1 and subtract it 2, and that removes the summation sign. So that's just a standard procedure. This is what I want to prove. This is what I want to prove at n minus 1. These two are true if and only if the difference is true, starting off from some trivial condition, which is the initial case. And that means I only have to prove something. I'm going to lose the n minus 1 case, but I only have to prove the following, that, and I clear denominators, dk gn squared is equal to this. That's what it suffices to prove. Now, I have to simplify that just a little bit. The biggest thing that can happen here is gn plus k minus 1. I'm going to replace that by the recursion. Now, this looks deceptively simple, but this is the whole point of the algebraic verification method. There's only one algebraic relation among these j and I. So I might as well use it and get rid of it, and that means I'm proving a pure statement about polynomials. The other thing is I'd like everything in terms of gn plus I, gn plus j. So what do I do with this I minus 1, j minus 1? Well, I'll just raise the coefficient ij, where I have I minus 1 and j minus 1. It'll be coefficient I plus 1, j plus 1 times gn plus I, gn plus j. In other words, I can rewrite this without the k minus 1. I'll just have to start at minus 1, and it'll be some crazy numbers, n prime ij times gn plus I, gn plus j. And again, I achieved that by taking what I wanted to prove for n, taking what I wanted to prove for n minus 1, subtracting them, just routine preparations, applying the recursion, because that's the only relationship we have, and unbundling this little sum here. And this is what I have left. And I have to prove this with the n prime ij, some linear combination of the nij. And as I said, the nice thing here is I have nothing to prove. That sounds counterintuitive, so let me just tell you why. So we are done. So this is not like a Perry. This is something really very simple. I have to verify for each I and j in these range that the coefficient here and the coefficient here, the coefficients on the left and right side, are equal. Now, that's not necessary, but it's certainly sufficient. I'm treating these as variables, though of course there are numbers that have specific meaning. And I'm saying I have a sum of, well, roughly k-squared items here, k-squared items here, except almost all of them are 0. If I show the coefficients are equal, then I've proven my result. So for each I and j, I have to prove this. When I is 0 and j is 0, I have to prove n prime 0, 0 is dk. When it's not, I have to prove n prime ij is 0. And you'll say, doesn't that require work? It doesn't. And the reason it doesn't is the n prime ij are 3 variable polynomials. They involve I, j, and k. Their degree is less than or equal to 2. So if you write any of them out, you have a second degree polynomial here and a second degree polynomial here. For example, dk is 2 times k minus 1. It's degree 1 and 1 variable. And what I actually do in the paper, because as I said, this is the proof, I'm done, is in making the simplifications, I had 5 summons. So I have a little 5 by 7 table. For I and j, there are 7 cases. I'll get to that in a second. For each one, I put in what the nij are. I sum them across, and then I just pick 2 of them and say, well, they're clearly 0. I look at the 0 one, and I say I'm done. So there's really nothing to do here, nothing to check by computer software. I mean, there are things to check, but it's just checking that 2 quadratic polynomials have the same coefficients. And I might mention a result that's not used that often. It was presented in 2003 in Scotland at the Fibonacci conference. Dressel presented his verification theorem. And his idea is if I have 2 Fibonacci-Lucas identities, well, you all know about the Binet form, alpha to the n is x, beta to the n is y. You get a polynomial in x and y, divide, if it's homogeneous, and he has a way of dealing with the non-homogeneous case, divide through by y to the n, and x over y is z. So you're proving that a polynomial is 0. And to prove a polynomial is 0 just means that you have to verify it at d plus 1 point. So he came out with the remarkable observation that if you want to prove a very complicated Fibonacci-Lucas identity, all you have to do is find its degree and check it at d plus 1 points. And that's the Dressel verification theorem. It hasn't been used too much, though. It was used in a recent paper by Melham. I'll get to it. It's very good for verifying a particular case in a family of identities. Now, I'm going a step beyond Dressel. I'm saying 2 polynomials are equal if the coefficients are equal. I don't have to verify anything. And that's what I just did. You expand that. I don't have time here, but if I had time, maybe 5 minutes, I'd expand something and I'd show you it is totally trivial. You just have 2 polynomials there. Now, there's one more problem here, which I skipped over. Suppose k goes to infinity here. Well, I have a lot of nij, right? I have k squared, I have O of k squared nij. So I have to check O of k squared things. It turns out that most of these n prime ij have the same form, and there are only 7 of them to check. And that took some work. Most of the verifications are the same. So the basic point here is, so let me tell you why. I'm not hiding anything like Perry did apparently, but when you simplify this, so if you're on the boundary, I minus 1, like if I is 0, so there is no minus 1 here. So on the boundary, these things are different. So I have to worry about the inside of the k minus 1 over k minus 1 rectangle, and I have to worry about the boundaries separate, and I have to worry about the boundaries of the boundaries, the boundary points separately. So here's a little picture of what you have to verify. So F is the inside, and all these nij look the same. D is the, so the triangle has 3 borders. This is the upper border, G is the rightmost border, and C is the diagonal border. And A is a corner point, E is a corner point, and A and E are different than D and G are different than F. And C is different, and B is different because remember, we want the coefficient of Gn squared is not 0. So I have 7 things to check, and all I did is make a 7 by 5 rectangle. For each of these cases, I had 5 summons because, I simplified everything, and I dumped into each one what the nij is. Then you sum across, and you have a polynomial in 3 variables, I, j, and k, and you have to show that equal to 0 or 2k minus 1, and that you just inspect it. There's no computer algebra or anything. So it was a very simple proof from the book, so to speak. And that completes that part of the proof. that part of the talk. Now what I want to do in the last 5 minutes is get to a possible new trend in identities. The reference for this is something I wrote in 2012. It wasn't a paper, it was a math review. So I'm quoting myself. It wasn't refereed, of course, but I outlined 5 stages, not necessarily consecutive, in the history of Fibonacci identities. When people started back in the 17th and 18th century, or going back to Fibonacci himself, so an identity was something cute, punchy, and unexpected. F of 2n equals ln fn. You don't expect that. And, you have to go prove it. And, there are lots of nice identities like that. Vajda, I think, in his appendix has 101. And Cauchy has, I don't know, yes. When he wrote his book, he gathered every paper ever written. And the nice thing about his book is that you have all these wonderful references. And he has all these, if you want to know all these identities, you'll find everything someplace. And that's really very nice. That's a stage, and we're still finding out very nice identities. Just open up the Fibonacci quarterly. Then we went through a stage called proof methods. The previous speaker alluded to that. If you can't prove things, use a method and see what you can get from it. One proof method is the Binet form. Another proof method is matrices. Another proof method is generating functions. Someone once mentioned mentioned a method of transforms. There are lots of methods. Each method makes things easy or hard for certain identities, and that was like a second stage. There was a third stage in which people got bored proving things for all n's. So they might prove things where the indices form an arithmetic progression or geometric progression, or maybe there are squares or things, and you can find lots of papers like that. A fourth stage, and I said these are not sequential. After a while you get bored with Fibonacci Lucas numbers, so you try things like the Catalan identity. Does that apply to the Pell Lucas numbers and the Lucas numbers? And does that apply when the recursion is not Fn equals Fn minus 1 plus Fn minus 2, but Fn equals AFn minus 1 plus BFn minus 2? And you look at the Catalan, the Cassini, the Cogne identities, and you say, can we generalize these for all things? So you're looking at recursive sequences, but very often you're sticking to order 2. And then a last stage that has emerged, in my opinion, in recent years is when you have families of identities and something is going to infinity. So what I want to suggest is the reason this 5th bullet we haven't seen that much of it is we don't have good proof methods. You give me an identity, I can prove it using the Binet form. If I can't do it, I'll throw it into some computer algebra system and I'll find the proof. And then, of course, if I post it on the Fibonacci quarterly, the challenge will be to find a simpler proof. And that happens. Or maybe there's a proof with matrices. But we don't have methods here. I'm going to try and show you on the next slide that methods are being developed. And I think this will be a trend in the next few years where we prove things for families of identities. So this is basically the papers I found on this. A very early work, well, not so early. Melham did quite a number of work. He's a Fibonaccian from Australia. He did fractions of sums, and the number of multiplicands in the denominator was increasing. And I don't see any special method there. In 2016, he had sums of nth powers of Fibonacci numbers, not what we did here today. The number of summands were going to infinity, but it's still a Fibonacci numbers. He generalized something, and he had a very nice generalization. He used Dressel verification for some very complicated cases that couldn't be done otherwise. So he proved it for 8 or 9 cases and said this must be true, but it's still an open conjecture. Prodinger and Selkirk used generating functions plus the Binet form. It's a very nice method. They proved f of k that way. They have explicit forms for the Binet form, and they involve computation with complex numbers. But if you're using computer algebra, if it's close enough to an integer, you can see it. And they can compute any particular k, but they can't do it uniformly for all k. And what we've shown in this talk is that the coefficients in the sum of square formulas has a very nice pattern, and their method would not allow that. It also requires a lot of computation, but we have the computational power. This is an old work of mine from 2019. Basically, I used the Tajiri identity And I looked at two products, and every time you have an Fn plus I, Fn plus J, I substituted what the Tajiri identity says. And I got a whole family of identities with the number of summands going to infinity. I'm more interested in the bottom part of this slide. I had a paper last year, so all of this is recent. I was looking at recursive triangles embedded in identity families. So I was looking at strange families of identities. The order of the recursion was going to infinity. And they had lots of zeros, and the zeros surrounded rows which were growing. So it was a triangle embedded inside an identity. And if you let the order of the identities go to infinity, the triangle grew, and the triangle had its own recursion. And the way I proved that is interesting. I used the Taylor series for, well, a Taylor series is a Taylor series, and every Taylor series has Taylor polynomials. Each Taylor polynomial is of finite degree, and it corresponds to the characteristic polynomial, which corresponds to the characteristic polynomial of that particular recursion. And using that, I was able to prove these things. So again, this is a different method. You've never seen a method like this, and I think it has a promise. This is an article that just was accepted in the Fibonacci Quarterly. I was looking at a recursion for this sequence, and here the indices, so these are the k-nacci numbers, but I'm not looking at 1, 2, 3, I'm looking at every kth number. So for the Fibonacci numbers, it'd be 0, F2, F4, F6, and that has a totally different recursion than the Fibonacci numbers itself. And the way I did this is I looked at the ideal of the characteristic polynomial, and I played some games with division and some concrete multiplication, but the point is no one's doing these things. By doing it that way, I could prove it uniformly for all k. And again, this is a method for proving things for a family of identities where the order of the recursion is going to a 0. And in this paper, I introduced the algebraic verification, which basically says if you only have one relationship and you get rid of that relationship, you're going to have left a collection of polynomials, and you can prove two polynomials are equal if their coefficients are the same without plugging in anything. So I think this portrays something to be done in the future. And I'll just mention, because a lot of these papers mention they can do anything. Prodinger-Selkirk did it, and just to prove it, they did the case 5. Melhem did it. In fact, the first time I read the paper, I thought he had proved it. Then I realized the conjecture was still open. There's a difference between any particular case and general case. So what Melhem did do is say, I have Dressel verification. You give me any k, and I will prove that case. But there's no uniform proof. What Prodinger-Selkirk said, you give me any particular k for the sum of the first n+1 k-nacci numbers, the generating function and Binet form I can write down, I'll prove something and I'll do it. But that will not prove it uniformly for all k. What we did in this paper is prove things for all k. So I hope that inspires people to go and change their attitude about identities. And thank you for listening.
All right. Thank you very much, Russell. We have to move on to the next talk, which will be